Alright, hello everyone. We are taking a look at not just measuring and classifying angles, but looking at diagrams involving angle pairs and using that information to set up an equation so that we can solve for either a variable or solve for the angle that we want to know. And then the second topic is to construct an angle and construct an angle bisector, and we'll do that on the next page. So in our previous lesson, we took a look at acute angles, right angles, obtuse angles, and straight angles. We're not really classifying them here, but you'll see those shapes represented within the diagrams. Yesterday we looked at naming angles, and now we're looking at how we can use these diagrams to build equations. Our first big idea today is this angle addition postulate. Now, we've had a postulate before. It was called the segment addition postulate. And the segment addition postulate was working with segments, of course, and I'm taking you back to the notes we had on that. And the segment addition postulate said that we could take a small segment, add it up with another small segment right next to it, and that total length would be the total. It makes sense that you can add up 10 plus 15 to get 25. What was tricky about it was using the names. We would have to add up by the names, so we would say the length of AB plus the length of BC equals the length of AC. We're looking at something very similar now, but with angles. And here's a diagram to get us started. Let's imagine that we have this angle on the top, and right next to it we have another angle. Here it happens to be below. Well, it makes sense we should be able to add these angles together to get the size of the total angle. That's the angle addition postulate. So you can see we have a large angle, and somewhere in between is a point P that is creating a third ray. Now, we're not saying it's bisecting. We're not saying that we have two congruent angles. We just have a ray that's somewhere in between the other two, and that's what this is describing. If point P is in the interior of angle RST, then the measure of angle RST, that big angle, is equal to the sum, because we're adding them up, the sum of the measures of those two smaller angles. So let's name them. We have an angle called angle RSP and an angle called PST. And here it's just restating that using an equation with the equal sign instead of just the words. So here we have the large angle. Again, notice we use little m for measurement because we'll be talking about numbers here. The measure of angle RST is equal to the sum, there's your plus sign, the sum of these other two angles. So we want to add up the measure of angle RSP and the measure of angle PST. It's usually easier to make sense of these things with numbers, so let's add some numbers to the diagram, and let's just pretend for a moment that this angle on the top is 10 degrees, and let's pretend that this angle here on the bottom is 20 degrees. So we would be adding up the 10-degree angle with the 20-degree angle, and it makes sense then that would equal the biggest angle, and the biggest angle is 30. So just picking some numbers there in a case like that. So let's take a look at a variety of different examples. We have 4 or 5 examples here on the first page just working with these angle pairs. We want to look for patterns and some differences between how the diagrams will have us set up the equation. So let's start off here with example 1. Here in example 1 it says, given that the measure of angle GFJ, that's the big one, is 155 degrees, then let's find the measure of angle GFH and the measure of angle HFJ. So you'll recognize in the diagram that the information they're giving us is not just a number but an expression. This angle on the right is represented by 4x minus 1. The angle on the left is represented by 4x plus 4. That means we have to first solve for x and then plug that number back in to get the size of the angle. So this problem has several steps. To make This information, a little bit more easy to view on the diagram, we're just going to put it in because it wasn't printed to begin with. We're talking about the big angle, angle GFJ, being 155 degrees. So this is the big angle, and so to make it stand out from these other two angles that are side by side, you can draw this arc, and if it helps, you can put little arrows on the arc to kind of say, hey, this whole size, this big angle, is the 155 degrees. So now we have all three angles information labeled on the diagram. So the angle addition postulate says we can take the small angle, add it to the other small angle that it's right next to, and that will equal the big angle. Now if I call them out by names, that would be the measure of angle GFH, that's the angle on the left, plus the measure of angle HFJ, that's the angle on the right, and that would equal the size of the big angle, which is the measure of angle GFJ. That's the angle addition postulate by the name of the angle, but we want to start solving with numbers, so let's do our substitution. This angle on the left is represented by the 4x plus 4. The angle on the right is 4x minus 1. Now we're adding these together, so there's a plus sign between those. And then that is equal to, they told us, the 155 degrees. So that's how we set up the equation. You'll notice in the diagram they have parentheses around the expression with that degree symbol on the outside. We could write it that way as well. We could put the parentheses around and put the degree symbol on there. But as our goal is to solve for x, we don't really have to have these extra pieces of information with the degree symbol. We could leave that out. We could leave these parentheses out as well because we're just combining like terms. So on the left hand side of the equation, 4x plus 4x is 8x, and 4 plus a negative 1 gives us a positive 3, so that equals 155. Let's move the constant terms to the right, so I'm subtracting 3 from both sides, so we have 8x on the left, that equals 152 on the right. So to isolate the variable, let's divide away the 8. We're dividing both sides by 8. And that means then that my x is 19. I used my calculator to figure that out. So that's a key step, but it's not the final answer, because what they want us to do is to find the specific angle measure. So what is the measure of angle GFH? Well, to find that out, we need to take the 19 and plug it back in for x. So angle GFH, that's the angle on the left, that's represented by 4x plus 4. So in place of x, I'm plugging in the 19. So it looks like 4 times 19 plus 4. And again, I can use my calculator here to help me out. That would be 80 degrees. And then the measure of angle HFJ. HFJ, that's the angle on the right. That's represented by the 4x minus 1. So 4 times the value of x, which is 19, and minus 1. Again, my calculator gives me 75. Now think for a moment. We're using the angle addition postulate. We're saying that these two angles should add up to the total. So do a quick check. Is it true that 80 plus 75 adds up to 155? And it sure does. So that's how we know we did the problem correctly. Example 2 is quite similar. We still have two angles that are next to each other, so this is our angle addition postulate. We'll be adding them up, and the given information tells us that angle VRS is a right angle, and in fact we can see the box right there, so we know it is. So we have to remember, by definition, a right angle is an angle with a measure of exactly 90 degrees. So even though they use the box, if you want, you can add to the diagram that the large angle is 90 degrees, and that's what we'll add up these two angles to. Again, we want to find both angles. The measure of angle VRT is represented by x minus 4. The measure of angle TRS is represented by 3x plus 2. So let's add up these two small angles and set it equal to the big angle. And I won't start with the names of the angles, we'll just go right to the numbers. So the angle on the left is the x minus 4. We have to add that up with the angle on the right, which is 3x plus 2, and we set that equal to the biggest angle, which is 90. So once again, our goal is to solve for x. Let's combine like terms. X plus 3x is 4x, and negative 4 plus 2 results in a negative 2. And let's move the constant terms to the other side of the equation. I'll add 2 to both sides. So we get 4x on the left and 92 on the right. Isolate the variable by dividing both sides by 4, and we get x equals 23. So again, that's a key step, but we're not done. Let's take that value and plug it back in to find the measure of the other two angles. So the measure of angle VRT, that's the x minus 4. I'll just drop in the value of 23 in place of x, so it looks like 23 minus 4, and that gives us 19 degrees. And the measure of angle TRS is the 3x plus 2. So 3 times the value of x of 23, so 3x plus 2. And my calculator helps me out to figure out that 71. So then do a quick check. Do they add up to 90 degrees? Because if they don't, that means we made a math mistake, and we'd have to go back and find that in our work. But they do add up to 90, so we're good. Here in example 3, we're stepping away from this angle addition postulate for a moment, and we're going back to yesterday when we were talking about the concept of congruent angles. Identify all pairs of congruent angles in the diagram. That's the first part. And then the second part, if the measure of angle P is 120 degrees, what is the measure of angle N? Alright, let's find the first part, all the pairs of congruent angles. So you'll notice that angle P has a single arc, angle N has a single arc, L has a double arc, M has a double arc. So we would pair up the singles with the singles and the doubles with the doubles. So up here at the top, you see that angle L will be congruent with angle M as they have the exact same symbol, the double arc. Here at the bottom of this, looks like a trapezoid, we have angle P is congruent with angle N because they have the exact same symbol. So remember, when we use congruency, there's no numbers, but now in this second part we're saying, but now we do have a number. Now we know that the measure of angle P is 120 degrees. That means we're going to transition from the congruent sign to the equal sign. And now that we have a number, we have to throw that little m in front. So we would say the measure of angle P equals the measure of angle N. Well, if angle P is 120 degrees, it makes sense that angle N is also 120 degrees because they have to be congruent. They are the same size. So these are all equal to each other. So we're saying the measure of angle P is 120, the measure of angle N is 120, and they are equal to each other. So we took a moment to talk about congruency because that's going to then feed into this next example. Here in example 4, we have a slightly different setup in our diagram. Here it says in the diagram, ray WY bisects angle XWZ. So here's the large angle XWZ. Ray WY is the angle bisector. It is cutting the big angle into half, and there you can see the arcs on either of those two angles that tell you they are the same size. So let's think about this. If these are the same size, then that means we can set them equal to each other. In other words, we're not adding them up to a total. Notice in the previous problems, these angles were not the same size. We did not set them equal to each other. No, we had to add them up to the largest angle. But if we have two congruent angles, like we do in example 4, well, I don't have to add them up unless they want me to find the total, and we will in a moment. Here we can start off by saying, hey, if the measure of angle XWY is 29 degrees, well then how big is angle YWZ? it has to be the same size. That's also 29 degrees. So in one sense, we're really starting with the idea that the measure of angle XWY equals the measure of angle YWZ. And we could say that they are congruent. Notice that is not the angle addition postulate because we did not add up two angles. However, to answer the final question, find the measure of angle XWZ, to find the big one, now this is the angle addition postulate because now we have to add up the two angles of 29. So the measure of angle XWZ is found by adding up the two angles that are 29 degrees. Here they happen to be the same size because we have the angle bisector, whereas in the previous examples they weren't the same size. So what we're trying to point out here is that when we have two angles that are the same size, that is created by an angle bisector. And that was told us right here when it said ray WY is bisecting the big angle. Whereas in answering the final question, that was using the property of the angle addition postulate. And I'll summarize that to fit it in the space. That's my angle addition postulate. Alright? So even though the numbers are pretty straightforward and not really much to solve for here, we're breaking it down with a very simple diagram before we get to this last one, because this is where, again, it's a little more complicated because there is no diagram. We have to create one ourselves. And we have to keep straight. What are we working with? Are we working with an angle bisector where the angles are the same size? Or are we working with the angle addition postulates where we have to add two angles together to get a bigger total? Let's see what happens in this last example. So in example 5, it says ray WY bisects. There's the key word right there. That means I have an angle bisector. That means I'm going to be working with something like this, where the two angles are the same size. I'm going to draw a picture because here's the big angle, and there's the angle bisector. So let's draw the big angle of angle XWZ. I don't really know whether it's acute or obtuse. We're just using a diagram to get our information onto the page. Now remember, that middle letter is your vertex of the angle. So because W is in the middle, we put W at the vertex. One of the rays gets the X, the other ray gets the Z. There's angle XWZ. This is the ray that is bisecting that angle, so we're starting at W and moving past point Y. So here's my third ray somewhere in the middle and moving past point Y. So there's the angle bisector. So because that's a bisector, mark your diagram with those arcs slightly offset. And now let's put into our diagram the information regarding the size in degrees. So our goal here is to find the measure of XWZ, which is the big one. That's our goal. And we're told that the measure of angle XWY, that's the one on the left, is X plus 13 degrees. Alright, label that inside the diagram. X plus 13 degrees. And the measure of angle YWZ, that's the angle on the right, is 3x minus 17 degrees. So now our picture is complete. That's our diagram. We have to figure out how to build an equation. Now again, the challenge here is, how do we set this up? Do we set it up like we did in example 1 and 2, where we had to add together the two angles that were side by side to get to some total? Is that what we do here? Do we add them together? Or do we set the two angles equal to each other because they happen to be the same size? And this is in fact what we must do because we have an angle bisector. That's our key word. Because of the bisector, we know the angles are the same size, and that's how we start. So I'm going to start by setting the angle on the left, the x plus 13, equal to the angle on the right, 3x minus 17, because they're the same size. So we did not add them together. So we have to solve for x here. Well, I have x on the left and 3x on the right. Let me move all my terms of x to the right. So I'm going to subtract x from both sides of the equation. That gives me 13 on the left, and on the right I have 2x minus 17. Let me move my constant terms to the left, so I will add 17 to both sides. So I get 30 on the left and 2x on the right. And then to isolate our variable, we'll divide away the 2. So that gives us 15. Okay, so now we'll take that, plug it back in, and then we will answer the question, which is to find the biggest angle. All right, so here the angle on the left is angle XWY. So the measure of angle XWY is the x plus 13. I'll plug in the value of x of 15. So that means 15 plus 13. That gives us a result of 28 degrees. Now that's not the final answer, that's just, we're getting close. The other angle on the right, angle YWZ, that is the 3x minus 17, so 3 times the value of x, plug in my 15, 3 times the 15 minus the 17. I get a little calculator work here, and I get 28 degrees. So again, this is a quick check to make sure that we set it up correctly up to this point. We are expecting them to be the same size. We said they would be because of the angle bisector. If they came out different sizes, that would be a problem. We'd have to go back and find our mistake. But they are correct, and so now we can finally answer the question, which is to find the angle, the big angle, angle XWZ. Well, it makes sense that if the angle on the left is 28 degrees and the angle on the right is 28 degrees, we're just going to add them together. And you're right, that's what we'll do. The measure of angle XWZ is found by adding them together. 28 plus 28, and that'll give us 56 degrees. So notice, in this very last step, this is the angle addition postulate. So we ended solving the problem with the angle addition postulate, and in contrast with the previous examples, we had to start with the angle addition postulate because we had two angles side by side that were different sizes. Here they happen to be the same size, so we set them equal to each other to solve. So those are our examples. Let's take a look at two constructions now. So if you will take your paper to the next side, we're going to use a compass and a straight edge, and I'll walk you through the steps here to first of all copy an angle, and then second of all to bisect an angle. So in this first construction, what we're calling construction number 3, if we want to copy an angle, then that means we have to have an angle to begin with that we want to duplicate. So that's where we'll start. So let's take our straight edge, and it could be any size. It could be acute, it could be right, it could be obtuse, it doesn't really matter. Let's just say that's an angle. We have no idea how many degrees there are. We're not measuring it. I know I have a protractor here, but the point is we're not using the rulers. We're not measuring it. What we want to do is we want to somehow like capture this and duplicate it over here using the idea that they will be congruent to each other, that they will be exactly the same. All right. So we need a way to kind of capture this space, this gap inside, without actually measuring it, and that's where our compass will come into play. So I know that my new angle, my duplicate angle, will also have a side, a ray, that's on the bottom. So I'm going to draw this on the bottom here. Now it doesn't matter how long it is because it's a ray. It goes on forever. So I'm making it a little bit bigger than what I actually need. The question is, where in the world do I put that second ray? We don't want to guesstimate and say, oh, it looks to be about in the same spot. We want to know precisely what is this gap, this spacing between the two rays. How do we capture that? So We're going to take our compass, we'll put the metal point at the vertex, and draw an arc that crosses over both rays. So the compass can be set open to any size, it doesn't really matter. We drew a single arc. I'm going to take that over to the new angle, and again draw an arc of the exact same size. Even though I don't know where that second ray will be placed, it'll cross this arc somewhere. And instead of taking a ruler, because we're not allowed to use rulers, instead of taking a ruler to find the distance between these 2 points of intersection, instead we're going to just use the compass, and we're going to reposition the sides so that they line up, and mine happen to be lined up pretty well already. But the idea is that even if it wasn't lined up, we would move the compass arms until they were positioned sort of spanning that distance between those 2 points of intersection. Alright, so there we have the distance that we've captured using the compass ends. We're going to transfer that over to the new angle. So there's my 1 point of intersection. I want my metal point to be there, and I'll use the pencil part to draw a little arc that crosses over the previous arc, and that will tell us the second point of intersection. So right about there is what we want. That's the second point of intersection. So those are the 2 points of intersection on the 2 angles, and that means that second ray has to go from the vertex through that second point of intersection. Using the straight edge, then we draw a ray right through that point of intersection, and there we go. So we have created 2 angles that are exactly the same size. So we would say angle A is congruent with angle B. And we could even put those little construction arcs inside. So with our final construction number 4, we are going to take an angle and we're going to bisect it precisely in half. So again, we're going to start off with an angle. It could be acute, it could be right, it could be obtuse. It doesn't really matter. Here I'll use an acute angle. And we'll call that angle A. So we can kind of estimate where the angle bisector would be. You can kind of eyeball where you think the halfway point would be to get 2 angles on either side of that ray that are the same size. But we want to create it precisely, and this is what we're going to do. We have 3 arcs that we have to draw. So you take your compass, put the metal point at the vertex, and draw our first arc, which will cross over the 2 rays. So we get now 2 points of intersection. We have a point of intersection on each ray. We're then going to keep the compass at the exact same setting. Don't make it bigger or smaller. We're going to draw 2 more arcs that are kind of here in the middle of the angle, and each of these 2 arcs will be positioned where the metal point of the compass is going to be at each of those 2 points of intersection. So setting that metal point down at one of those points of intersection, here is one of the arcs. And then don't change the setting on your compass, just reposition it now so that the metal point is at the other point of intersection on the other ray. Draw that 3rd arc now so it's overlapping the 2nd. And now what we have is a point that is smack dab in between the 2 angle sides. And we know it's exactly in the middle because we kept the size of the compass the same for each time we drew an arc. So there's the point of intersection for our angle bisector. So draw a straight ray from the vertex at A through that 3rd point of intersection. And now we have 2 angles that are exactly the same size. And so that we can name these, let me put a few more letters on my diagram. So here's B, here's C, and here's D. So we will say angle BAC is congruent with angle CAD. And we've bisected it exactly. that's the end of our lesson. When we come back next time, we'll be stepping away from angles for a moment and take a look at simplifying radicals so that we can then get to working with the Pythagorean theorem, which has to do with right angles in right triangles.